So first lesson here we will talk about how do you estimate the cost, and the lesson after that we will talk about how do you reduce the cost. Where are the cost reduction opportunities really in a foundry by manufacturing, and later on by design. So within estimation we will look at the tool cost estimation, where we will spend little more time, and later on we will look at material cost estimation, energy cost estimation, labor and overheads, which we will do it little more in passing. So to start with, if you look at cost estimation techniques, there are several techniques which are used by accountants and financial managers. What we have is a history base, where they have historical data and from that they can extrapolate or even interpolate. Okay. But the one which is really becoming more popular today is called as ABC, or activity based costing, where you are looking at what is the life cycle of a component or a part or a product, what are the different activities in that, and each activity what are the tasks in that, and each task what are the inputs going in terms of material, labor, energy, and sometimes they make it a little dirty by saying overheads also, but you are not supposed to put overheads in ABC, because you break it down everything into the finely in terms of resources which go only in that activity, new materials or new energy or new labor or whatever. But there is another method which is very useful for designing point of view, where you do not look at resources, but you look at you don't even look at cost elements. In fact, you look at what are the design parameters which affect my cost. So if you say a pump cost, maybe a function of its weight, or it could be a function of its power, or maybe its rating, things like that, which are nothing to do with cost directly but indirectly. So design parameters linked to cost, and how do you give weightages or coefficients to those parameters is referred to as is your parametric based cost estimation. So these are three different techniques of cost estimation. One is as purely financial, second is more like process planning and resource planning kind of a thing, and third one is purely from design parameter based costing. Which is good, which is bad for metal casting? There is no direct answer. Different things are useful for different situations. In fact, we have used a mix of the three techniques depending on which is more easily applicable and inputs are easily available, and it gives fairly accurate and fairly acceptable results. Now before I go into the models, cost models, we also have to understand and appreciate that the data for cost models is as important as the equation which we use in the cost model, and these data can be standard data which keeps changing all the time, like material rate or labor rate or energy rate, and we have to put the values of that. We also have to worry about adjusting those values for your let's say if you have the inflation has occurred over a period of time, or let's say some new technology has come which makes my labor rate or equipment overheads drastically different. So I need to adjust for those values. I need to have some baseline here. Finally we have to also normalize the values. So how do you get the data from? Okay, you get the data from all the way from accounting and historical records to all the way from subject experts and domain experts, especially those rates and adjustments and all that. You need to access experts for that. Okay, what are the major elements of costing? One is tooling, and we always treat tooling specially because depending on who pays for tooling, either the whole tooling is paid for or you amortize the tooling cost over production, over the life of the tooling. So there are two different ways. So we just estimate tooling cost separately in beginning, and you can later on use it any way you want to use. Then the actual production, you have material and the conversion cost, and conversion cost again you look at energy and melting and then labor and overheads and so on. And then later on we mention a little bit about modifiers. You have to worry about what are the cost modifiers. So yield or rejection rate, these are modifiers to the cost, and you need to worry about what are the values for that. Okay, so the big picture of casting cost estimation looks like this. On the left side you have the casting process plan, and that is what you are most comfortable with. On the left side you have the casting process plan, and process plan itself you see on top. You don't have to do it for every project. If you can use like the way they do it in machining, you must have heard about generative process planning and variant process planning and so on. You can apply the same principles to metal casting also, and by doing that you can quickly develop a reasonably good process plan, a reasonably starting process plan for a new project. very good when you have, let us say, making copper valves and you have a new valve, and that process plan you can map it from a previous copper valve which is of same weight and same number of cores and so on and so forth. Then you also see on the left side methoding data coming out, and for methoding data also can be from a, you may have standard riser sizes, standard sprue sizes, standard filters and so on, or standard sleeves, which you can also pull from database. So you don't have to reinvent the wheel for every new casting if you already done something similar previously. These are the good practices for doing it fast. Now on the right side, if you see, very right side, you see the part design details. So there you need to have all the, your like what is the metal, what is the your process, what are wall thickness and weight and all those things. And you see in the middle some of those values coming from the left side to right side, where you finally compute what is the direct metal cost. Indirect material cost is like mold and core and maybe consumables like sleeves or filters, and then labor, energy, tooling, and finally overhead. So now we'll show you a few slides of how to estimate these. Now not all of them are rocket science, so we hesitate to show too much of costing to practical business people, so it's embarrassing. So we'll kind of focus on something where there is a little bit of scientific input from our side. The first one, before we do anything else, I mentioned process planning in passing, but we recommend usually that process plan itself can be broken into 3 steps. You talk about pre-casting activities, and then actual casting activities, and then the post-casting activities. And for each activity you break it down into tasks. For example, this is not exhaustive list. For example, pre-casting can include core making and mold making. Actual casting can include melting, holding and pouring and so on. And post-casting can include things like shakeout and fettling and perhaps cleaning. Okay, I'm not talking about other post-casting like heat treatment and machining and painting and things, shipping and all that. And for each task you have to worry about what is the method. These are standardized ways of making a what is called as methods card, but methods card is not just method, it has to be, ideally you should say casting process plan, and that's a better definition of what you. And remember, you have, once you choose a process or once you choose a method for a particular task, it also note down what are the parameters. Why you need that? You need to write down the steps which a foundry man or a shop floor worker has to follow. That is steps. You also have to list in that what are the parameters and what are the correct values of parameters which become quality checks. The rule of the game today is don't do quality check after the entire thing has been made. You do quality check at every step. Catch a problem before it occurs much before you spend much more money and time wasting on making a defective casting which you know is going to be defective because some process went wrong at some point of time. So quality checks, in process quality checks is the name of the game today. I don't know how many of you are follow, but you're following in a systematic way is also not easy, and it has to have a lot of discipline. Why I'm saying all those things, this process plan, detailed process plan is a major input for your cost estimation. And remember, we mentioned also that we want to cost estimate design stage. How will the designers know all the process plan? So unless process planning itself is systematized and there is a nice program for that, and or there are templates for making a process plan for previous similar casting, they can quickly map it to that to a new casting. Okay, so this is an important input for designers also. Now here is the big mantra, again comes from Dr. Durgesh, who spent a good amount of time talking to 2 tool makers from 2 different places in India, and he gave them, you remember those 40 different shapes we looked at, the shape complexity, he gave those shapes to them. The tool makers spent a lot of time over months designing the tooling for those parts and then estimating the cost of those toolings, the actual manufactured cost of those toolings. With that data, he did what is called as a regression analysis to generate these numbers which you see. We have already done those ratios, volume ratio, area ratio, number of cores, core volume ratio and thickness ratio, but now we are putting a value to that. Earlier we did a averaging of the values of those ratios. Yeah. What are the inputs and what are the outputs? Simple. Inputs are these ratios, these 5 numbers, which you can get for a particular part. We have 40 parts. For each part you calculate these 5 parameters. And for that part you already have the tool cost. Because 2 people have estimated, you take average value of that, so you know reasonably they are reasonable number there. Then you run a mathematical program called regression analysis, which is also available in Excel these days. And once you do that, it fits these numbers, these coefficients which you see in red here, so that using the parameters and these coefficients, you get the tool cost as close to what was estimated as possible. In other words, from a practical point of view, if you have any new part on a wide range of complexity in the range which we have seen, and we have taken a very simple L shape to all the way to a engine block or a gear casing or a manifold kind of a complexity. So you take any new part, you calculate for the part, you have the volume, surface area, thicknesses and all that, number of cores and core volume. You can make those parameters and multiply by those coefficients, and I will show you the next slide, multiply by the cost of making a simple tool. You can estimate a tooling cost without doing any tooling machining planning, tooling process planning. Let me show you actually. So go ahead.
Here the quotients means the importance of each thing you are taking.
Yes.
Area ratio is given more importance.
Yes.
That's why the quotient
Yes.
is that.
Yes. Yes. You can say that, and I was going to say the same thing. If you see the ratios here, area ratio gets the highest thing, followed immediately by number of cores, and you are not surprised. We did say number of cores does make life more complex for a foundry people. Okay, followed immediately by part volume ratio, then core volume ratio also. Thickness ratio you can even ignore, it's not going to give you a lot of inaccuracy. So you can even manage with the first 4 numbers here. Now let's actually apply it to a real life. First quickly, what we can now redefine shape complexity as, and that answers your question also, we can redefine shape complexity as the actual tooling machine cost by the cost of machining a cube of the same volume. So cost of machining a cube versus cost of machining a complicated shape with the same volume, that ratio is shape complexity now. This is my real practical shape complexity. What we did earlier was theoretical shape complexity in those 5 parameters. So I run the regression analysis by matching the 2 complexities, and therefore I get those coefficient values. Okay. And what we did was we took 3 additional shapes which were not in the original analysis. Okay. And then if you see, you have actual values of at the end of the top table, you say complexity factor estimated from a CAD program. How do you estimate that? Calculate those 5 ratios and core 3 ratios plus core number and core volume ratio, and put the coefficient values. You get 47, 35, 37 numbers there. Then we also told the same tool people, now tell me what is the actual tooling cost for those 3 parts. Okay, and they said the actual cost in, let's say, rupees is the first column on the bottom table. So 71,000, 1.58 lakhs, and then 20,000 rupees. And then if you see the next one, we also ask them what would be the cost of machining a cube of the same volume, which is simply depends on your cube volume and your some machining rate. You can say 10 paise per centimeter cube or something like that. Okay, and that is your complexity factor actual, which comes from the tool makers, which indicates how many times the cost increased because the shape became more complicated from a cube. Now look at the difference between the actual and the estimated. Estimated is from the same top table. Hardly 2-3% error. In fact, when he showed the data to me first time, I said, oh, less than 5% error sounds too good to be true. You don't get that kind of results anywhere in any analysis. But it was with 40 examples and 3 random cases, we got a very good result. Remember, this is for metal tooling for sand casting process. Later on, someone said, can you estimate tooling like this for injection molding? Someone said later on, die casting, can you do that? Yes, it is possible, except that we have to run the exercise all over again. Take again maybe 40 shapes which are common to die casting, go to some 2 or 3 tool makers, ask the cost to them, but now we have a scientific way of estimating the tooling cost directly from the CAD model of the part. We do not need any information, and this takes less than 1 second. So now I am just going to go through some slides quickly. I will not go into details. So on the top you just see in orange what is the equation meant for. So here you see the total tooling cost, so tool material cost, and we are taking some simple example, and if you look at order quantity, you can divide that and you get a tooling cost per part, amortized cost. Similar tool manufacturing cost from the shape complexity equation. Here we are assuming the machining rate is about 0.1 rupees per centimeter cube, and you can get tooling costs somewhat like that. Amortized cost of tooling manufacturing is 12 rupees. Similarly, direct cost, this is a cast metal which actually goes to the customer. Okay, obviously little bit 5-10% extra weight, but it goes to customer anyway. Cost of that, you can adjust it little bit, saying that okay, I am to produce little extra castings because of rejections, or to produce pour some extra metal because my metal is lost by oxidation and things like that. So some adjustments, and I can say okay, finally is so much. And then you are looking at indirect material costs like mold and core, and you can also add as filters and sleeves and all that. But remember, mold and core may be recycled, so you have to put that recycling factor there. So here you are assuming that mold recycling is 80%, for example. So because customer is not paying for 80% mold cost, he is only paying for 20% of the mold material cost, which is lost in the process. So you get some rupees here, and then you look at indirect material, some more indirect material like core, okay, and as I said, you can add something else. Now this, let me spend a minute on energy cost. Now energy cost can be estimated. Many people already have saying my melting cost is so many units per kg of metal, aluminum or iron or ferrous, and usually you will find that if you have done it properly, usually both of them have almost similar melting energy. Although pouring temperature is low for aluminum by half, the specific heat of aluminum is so high that, and latent heat is so high that finally the unit cost for either aluminum or steel or iron is almost same, roughly almost close to 1 unit. So you are not doing too much error by doing that. But here you can actually estimate the cost a little more accurately, and it does make sense. The pouring temperature is a little more high, or holding time is more high, you can incorporate holding time in this, and you can say I have additional energy cost because of that. Now one trick we have used and we recommend to foundries is, what about other energy costs? Cost in mold making and core making and fettling and so on. Okay. Now you can't go around estimating every cost, and that's too painful for that. So what we do is, we say is, you do energy audit of your foundry over a period of time, over a 1 year period of time, and you will find that okay, in a year I am consuming, let's say, 1 million units of energy, and you find that surprise, my melting energy is roughly more or less between 40 to 45% of the total energy cost, which is really true in about half, 40 to 50% in a real foundry. Maybe yours is 80% in a foundry if it's a manual foundry. If you have high automation, you have automatic disarmatic lines and all those things, then energy costs can go up a little bit more, and you have automatic fettling. So it depends on the level of automation really. So automatic foundries can go up, can energy cost, melting cost can be, proportion can be less, about 55% or so. So if you estimate melting costs accurately, okay, and you say my other costs are my energy cost is 80%, other costs are 20%, you can quickly estimate the total energy cost. It's a far more easy way to get reasonably accurate estimation. I mean, don't put a very complicated equation when you need the whole weightage of that is only 5% of the whole thing. So you be as accurate in what is more important. So energy cost is the most important thing, and you can estimate accurately based upon this. Only recommendation here is that you can add the holding time and holding energy cost also. So that is your energy cost, and total energy cost, as I said, you can take a fraction, and we took it as 50%, so that's easy to calculate. Otherwise you say 50%, you get confused here, but you can say 80% in your case. Now labor cost, how much really I should estimate? I mean, fortunately or unfortunately, either way you want to look at it, the labor cost as a proportion of the total cost is not so high. So one way to estimate is saying that tell me the total man hours which go into making this casting, and you can do it in different ways. You can look at again historically saying that okay, you can say you can make it as a function of casting weight and shape complexity, easiest way. So you can say that you can have a small table, you can say per kg labor input rate for a simple shape or medium shape or high complex shape is so much. Or if you want to put complexity as a graph, you can make a graph of weight and complexity and then draw a nice graph saying my labor hours per kg of casting is so much. Okay, and with that we would say it's good enough, and you can get the labor rate per kg of casting or per casting finally. And then you have other processes like you may have heat treatment and inspection, fettling and few other things. You can make it usually again as a function of casting weight. We keep saying that also please include one more factor saying casting shape complexity, and I'll tell you that OEMs will appreciate that. I mean, they will not at least argue with you that on that. Okay, so you can say weight and shape complexity, or you can adjust the weight saying it is 1 kg weight only, but my actually thing is actually equivalent to 3 kg because its shape is more complex. Okay. So finally I get my other things. Overheads you can take overall and then again do it by weight basis and again shape complexity basis. And finally you can, for the calculation which I showed you, it is a simple part, so you can see that the material cost is really almost 2/3. In a more complex casting you will find material cost proportion will be much less. Total cost will be more, but the proportion of material cost may be half or less than half or 1/3 or even less. Higher the your competence and core competence and higher the quality requirement, your value addition becomes more. Here value addition is hardly 30%. Okay, to summarize, we have just looked at very quickly how to estimate the cost in a foundry without really doing too much of detailed foundry process planning. You can cut and paste an old process plan and you can use some smart tricks to relate the cost with the part design. That's what we have done. So done a little bit of mix the three methods: history based method, activity based method, and the parametric method also. The tooling cost was an example of parametric method. Okay, so we used the three methods in combination to come with a cost model which is very easy to apply. You can automate the costing to a second. If you have the part CAD drawing, you can estimate tooling cost in a second. But the idea is to use cost estimation not as much for quoting or negotiation purpose, but as more like a DFM tool. A designer can use this to see between two design alternatives. Of course, you can use it to compare two different methoding alternatives, which is the more economical one. Okay.